Okay, so far in the course we've talked about basically resistors and voltage sources, resistors and batteries. We've got a lot of ground out of that. We've covered a lot of stuff, but we're going to start moving on and broadening our horizons and talking about some new circuit elements. And we'll talk today about capacitors and inductors. Now, a capacitor is something with a well-defined capacitance. An inductor is something with a well-defined inductance. So we'll talk briefly about, for example, what capacitance means, and then we'll get into the devices themselves. So what is capacitance? Let's say we have a potential difference across, say, two surfaces, and for simplicity we'll say there's just a gap between these two surfaces such that no current can flow. So I'll try to sketch that here. We have surface 1, surface 2, and somehow, through hook or crook, there is a potential difference across this gap here. Something had to cause that potential difference. Some charge distribution has to be set up to create that potential difference. There's going to be an electric field, and that electric field corresponds to a voltage. So the question of capacitance is, given that voltage, how many charges do I get? Or given that charge distribution, what voltage does that correspond to? And that is the definition of capacitance. So capacitance is the capability of something to store charge. Specifically, the capacitance is the amount of charge I get for a given voltage, Q over V. And the units of capacitance is farads. Now, in electronics, we often talk about capacitance in terms of currents, right? We don't really talk about how many coulombs I have in my circuit. We're more interested in how many coulombs per second, or amps, I have in my circuit. So we need to relate this to the more fundamental quantities that we see in electronics. And there's a kind of a good model to understand this is, imagine we had two parallel plates of metal and we put them close together. This is going to be our canonical capacitor that's going to allow us to understand capacitance. We'll hook that up to a voltage via a battery. So let's sketch what I mean by that. This is the common way of thinking about capacitance. Okay, so we have a voltage V. These wires here are equipotential, so they maintain the same voltage throughout this wire. It's V volts, and it's 0 volts all the way across this other wire. And let's see what happens. Imagine we just turn this battery on. Well, I have some negative charges, some electrons, and they are disgusted by the negative end of this battery. They're repulsed by it, and they're going to go as far away as possible from it. So we might get a negative charge here and there. Where are they coming from? They're going to have to go through the circuit somehow. So I'm going to get a positive set of charges on the other side of this plate here. And as we do this, we can see what we're actually doing here. We're drawing charges per unit time, or current, through the circuit. So by convention, that means the current is going this way. And as that current is flowing, we actually have positive charges accumulating on this surface, which creates its own voltage source. Now we can relate the capacitance to the current and understand the kind of dynamics, the time dynamics of how this scenario happens. So let's take our above equation and we'll rewrite it. Right, Q is equal to C times V. And what we'll do is we'll take the time derivative of this, dq by dt, which is also known as the current, I. And what's that equal to? Well, the capacitance is just a material property. It's going to be constant. It's how much a particular geometry can, or how much charge a particular geometry can store. And the voltage is what's going to have to change as the current changes. Okay. Now there's one thing we have to be careful about here. So this is probably the more important way of thinking about capacitance for our course. But we have to be a bit careful about the sign here. Let's think about this. If I have a current which is flowing to the right, which way is the voltage going? So as the current is flowing to the right here, as I'm going along the current, I'm actually going from a higher to a lower potential across the capacitor. So I technically have to put a minus sign in this equation, right? So as I'm going from left to right here, I'm dropping voltage. I get a negative dV as charges are accumulating So I get a dq by dt, and then a voltage is building up which opposes that current. All right? Subtle point, but an important one. And both C is equal to Q over V and I is equal to negative C dV by dt are very important equations. We're going to use the second one most in this course. So that's capacitance. For our purposes, we'll see actually in electromagnetism, we think about capacitors mostly as charge storing devices or storing energy in the electric field. For electronics, we're actually going to see these things as frequency-dependent resistors in some sense. We'll learn about that in part 2. So let's look at capacitors. Let's look at capacitors now that we know what capacitance is. So if you recall from before with resistors, I'll just jot this down, we had a formula for resistors for a very particular convenient geometry. A resistor is something with a well-defined resistance. And if we had a tube of length L and area A, that tube was made out of a material that had a resistivity rho. And we could write down a geometric formula for the resistance. It was rho L over A. That's what R was. So let's think about how we can calculate a similar formula for the capacitance instead of the resistance. So we're going to have to go back into our memory banks and remember a fact of electromagnetism. Namely, that if we have a big piece of metal, a flat plane, and it has a given charge per area, we'll say a constant Q over A, a charge surface density, or surface charge density, rather, that corresponds to a very particular electric field, a constant electric field, pointing out of the surface with magnitude of the charge density, Q over A, times 1 over epsilon. And it is a vector, so it happens to be pointing normal to the surface. So what is epsilon? Well, epsilon is a material property, the same way that rho was for copper or silicon. But what is epsilon? Well, epsilon is a material property, just like rho was for resistance. For air at some value, for plastic at some other value. Epsilon is called the permittivity. And if we happen to be in a vacuum, we have a particular value of permittivity, the permittivity of free space, which is a constant of nature. 8.85 times 10 to the minus 12 farads per meter, approximately, in vacuum, and approximately in air too. So it's just some material property. For plastic, it might be 2 or 3 times that. So let's use this now to the above situation. We've charged up 2 plates of metal that are facing each other, separated by a distance d. Well, in this case, let's see what we get. Here, we have, we'll zoom in here. We have 2 plates, and each one of them produces a field. The red one produces a field that's constant roughly across that area, as long as the area is big compared to the distance. So around the edges, the field might be a bit curved, but near the center, it's going to be roughly constant, and it's going to have a value of, I messed up the above formula. Let's just go back. No edits. Let's just go back. Epsilon, it's the field given by this parallel plate is Q over 2 epsilon A. I apologize for that. So it's going to be 1/2 Q due to the positive charges. The negative charges on the other side will also lead to the same field. It's pointing the other way, but the charges are negative. So we're going to have the same field, and we basically double that value. Now, psychologically, I subliminally removed the 2 because I knew I was going to double it in the end. That is a flaw. when you're thinking and talking at the same time, so I apologize. But the electric field we get is equal to Q over epsilon A, the magnitude of it. All right, we know which direction it's pointing. Good, okay. But we want to relate this to electronics quantities, voltages, and things like that. So remember Ed's formula. E times D is the voltage when you have a constant electric field. So we can write this as the voltage divided by the distance between them. And we're actually here already, because if we recall, we have this definition. I'll just rewrite it. We have the capacitance is the charge per volt. Both of those things we have here, Q and V. So we actually can write down our expression for capacitance. Now we can write that using these terms here as follows. Q over V is equal to epsilon A over D. So we have our equation for the capacitance, the geometric equation for the capacitance of something when you have a piece of plastic of permittivity epsilon separating two conductors of area A separated by distance D. We have a capacitance is equal to epsilon A over D. Now compare that to, just to recall, compare that to the case for resistors, where it was rho D over A. So it's kind of the opposite. The bigger the area, the larger the capacitance. The bigger the area meant a smaller resistance. Okay, so that's what a capacitor is. Now let's very quickly talk about how to think about these things in a circuit. So a resistor, we had a cartoon. All right, okay, so let's move on and talk about capacitors in a circuit. Let's actually zero in on this process of charging the capacitor. As we're doing this, we're running current that is building up on the plates and eventually creating its own voltage pointing in the other way. But we're moving charges one by one. And the amount of charges per second tells how fast we can do this. And what we can do is we can put in a resistor and limit the rate of charges that are charging up these two plates. So let's do this. We're going to make an arrangement here. We're going to make this funny arrangement where we have a battery that's going to be connected to a resistor, and then we're going to move it to a capacitor. I haven't told you how to draw a capacitor yet, have I? Well, the circuit diagram for a capacitor is kind of a cartoon of what it is. This is the circuit diagram of a capacitor. It looks slightly like a resistor, but we have parallel plates that are the same length here. So it's supposed to be a cartoon of two parallel plates. So we'll put our capacitor here with capacitance C, and we will complete the circuit. But what we're going to do is we're actually going to put a switch, which can go one way or the other. It can be connected to the right, in which case we have a battery in our circuit, or it can be connected to the left, in which case we just have a capacitor and a resistor. And we're going to use this to study what the process is and how the charge and voltages in the circuit vary as this charging is happening. So let's say initially that it's connected. We're going to connect it, and our circuit looks like this. We have current flowing all the way around the circuit, but only so much current is going to flow, because as soon as I get enough electrons that have flown to build up a charge that opposes the voltage of the battery, remember we're building up a delta V here, this thing is completely charged. In fact, let's write this down. Let's use a Kirchhoff loop, a Kirchhoffian voltage loop, and travel around the circuit. So we'll see that the voltage of the battery plus the voltage of the resistor plus the voltage of the capacitor have to add up to 0, right? And we already know what the voltage drop across the resistor is. It's IR. And that's equal to negative voltage drop across the capacitor. But we're going to work in the so-called steady state. We'll turn it on and we'll wait for it to, all the electrons to go through and sit on that capacitor such that the voltage of the capacitor completely balances that of the battery, and we have no more current. Well, in that case, we have the voltage on the capacitor is equal and opposite to that of the battery. So let's pretend we just did that. For all times less than some arbitrary t equals 0, we connect the battery to the point where we have negative VC. We have negative VC across that capacitor there. So let's say we've done that. And then at time t is equal to 0, we're going to switch over. So we'll close that switch, and that battery is no longer in the picture. There's nothing connected here. So it's basically just sitting there doing nothing. And our circuit looks much simpler. We have a resistance. Let's just abstractly call it R. And a capacitor with some voltage across it. So we have voltage of the capacitor as a function of time, and we want to know what that is. But we know that the voltage at the capacitor right at time equals 0 is negative voltage of the battery. So what does work now in units like this? We'll be careful to keep track of the signs, and we'll say, let's pay attention to the current going this way. So that's going to be equal to V naught. Some V naught, V of the battery, that happens to be the battery at t equals 0, technically negative voltage of the battery. And we just have an initial condition. Let's again apply Kirchhoff's laws. Kirchhoff's voltage law. Let's go around this green loop here and see what we find. Well, now we have V, the voltage of the capacitor as a function of time, minus, we're subtracting, IR is equal to 0, or V is equal to IR. Okay, looks like we're in trouble here. Where do we go from here? Well, we at first notice that the current is a function of time, right? I of t. Because initially it's going to start flowing, but the capacitor will drain itself of charge eventually. How do we proceed? Well, we can use our equation above. We'll use the fact, I'll just redraw it. We'll use the fact that I of t, dq by dt, is equal to negative c dv, that's specifically the voltage across the capacitor, as a function of time. Okay, we've done that now. And this is technically, by the way, we have to be careful, this is technically the current through the capacitor. But since there's only one path in the circuit for current to go, well, in that case, that's the same as through the resistor. So we can actually use that I of t in this equation. And let's see what we get when we do that. We have V of c of t is equal to negative c dv, c by dt, times r. This is what we call a differential equation. So write it slightly differently. dv by dt is equal to negative rc, negative 1 over rc times v. Or there's many ways to solve this equation, but let's write it like this. dv over v is equal to negative dt over rc. This is interesting. So in the left side we have units of, it's unitless. dv has the same units as v. And the right-hand side, therefore, has to be unitless. That means resistance times capacitance has units of time, which is weird. So if you want to say you want to meet someone in 10 seconds, and you want to be a jerk, you can say, meet me in 10 ohm farads. And that's the same thing. So let's integrate both sides of this in the standard approach to solving this kinds of differential equations, and we get the natural log of the voltage is equal to negative t over rc plus some arbitrary constant. We raise both sides to the power of e, and e to the ln v, well, that's just v of t is equal to some other constant. Well, let's just write it out. E to the minus t over rc times e to the some constant, and e to the constant is just some other constant. So we'll just call it k. And that's our solution to our differential equation. But we also know that at t equals 0, where this is e to the 0 times k, also known as K. Well, that's a given value. That's V naught, voltage of the battery, whatever it started out to be. So that we have our solution to the capacitor, which is draining itself or discharging, as follows. V of t is equal to V naught e to the minus t over RC. That's the equation for discharging a capacitor. So if we plot it, let's plot it here. It would start out at t equals 0 at V naught, and it would be an exponential decay down to 0. It would never get to a 0 mathematically, but it would be an exponential decay, right? In fact, it would get to a very specific value. What we're doing here, by the way, we're plotting voltage versus time. I should probably say that. At a very specific value, it's going to get to V naught over E. That's approximately equal to 0.63 times V naught. At that particular value, we have, so at that very special time, we'll call that time tau. At that special time, we have V naught e to the minus tau, V naught e to the minus tau over RC is equal to V naught e to the minus 1, or tau is equal to RC. So if we're measuring, if we're flicking the switch and watching the capacitor discharge, and we wait for it to get to about 63% of its maximum value, we just measure that time, and that's a very special time. That gives us the time equal to RC. If we know the resistor, by the way, this is a great way to measure the capacitance. I measure 1 millisecond. I have a 1 kilo ohm resistor. This is a great way to measure the capacitance, which in this example would have been 1 microfarad. Pretty typical capacitance, actually. All right, so what does a capacitor actually look like in a circuit? Well, I have a few of them on me. There's a number of different types of capacitors. We have thin film and ceramic capacitors. Here's a thin film and a ceramic, or thin film capacitor right here. I just have them on my desk. And this is a value of 47 nanofarads. We have these so-called electrolytic capacitors, and this is 470 microfarads, so just about half of a millifarad. There's also surface mount versions. So I have a 1 nanofarad, I believe, if I remember, surface mount capacitor right here. Tiny, like little fleck of dust. And then there's this monstrosity that I found in the hallway here. This is a 3.5 farad capacitor. There's more. We have these super caps, which is about the same capacitance, but in a much smaller package. So there's a lot of these capacitors. Some of these electrolytic ones, and the super capacitor included, are polarized. That means you have to put them in a certain way, because the way they work, there's an oxide layer that builds up when you put the voltage a certain way that forms part of that capacitive barrier. Let's actually plug, maybe not the supercapacitor because I'm too terrified. Let's plug something like this in the wrong way and see what happens. Okay, so I have a 10 microfarad capacitor here rated for 63 volts. We will put 63 volts across it, but we'll violate the polarity. We'll put it through the wrong way, and we'll see if anything exciting happens when we do it. Yeah, so it didn't like it too much. Here's what's left of the capacitor. So polarity matters with electrolytics. Okay, that was fun. So let's just finish this off. We can also look at the other way, the other side of things. We can charge a capacitor. Doing so, we get a very similar differential equation we can solve. If we just do let's just draw what we get. when we do this, we can do our Kirchhoffian loop rather, and we can say that V minus IR plus the voltage of the capacitor should equal to 0. And as we're charging it up now, we can actually solve the same differential equation as we did before, but with an extra term. It's called an inhomogeneous differential equation. And we'll get something very similar. We'll get V naught times 1 minus e to the minus t over RC. And that looks similar, except it asymptotically approaches. That's how you charge a capacitor. This is discharging. We get an exponential asymptotic approach to V naught in the case of charging, and an asymptotic approach as an exponential drop to 0 in the case of discharging. So that's the time dynamics of how you use capacitors. Okay, the last thing I want to talk about in terms of capacitors is the energy stored in a capacitor. So let's look at that. The energy stored in a capacitor. And remember, we're going to use energy U for the symbol for energy, because E is already taken for, lowercase e is taken for the elementary charge. Uppercase E is already taken for electric field. It would get very confusing, so we use U. Now, during the process of charging this capacitor, we've basically moved a little charge, say delta Q, a little mini charge across a voltage V. How much energy does that correspond to? Well, by definition, voltage is the energy per unit charge. So that corresponds to a given amount of energy, delta U, of V times delta Q, by definition. Now we'll make this infinitesimally small. So we'll basically curl over those deltas and or uncurl them and write, we get a small infinitesimal change in energy, which is V times a small infinitesimal change in charge. Now imagine we're going to do this again and again and again and again and charge up this capacitor. How much energy are we storing? Well, as we do that, we're adding all the small infinitesimal elements up. What is a word for adding small infinitesimal elements up? That becomes an integral. So the total energy we get by integrating this infinitesimal energy up. Okay, we're almost done, but we have to be a bit careful. V is not a constant. As we add more and more charge, we're changing what V is, but luckily we have a formula for it. It's equal to, when we have, let me just write this down, C is equal to Q over V. So V is Q over C. So we have 1 over C integral of Q times dq. Okay, that's good. That's actually an easy one to do. The integral of Q dq is the integral of x dx, which is 1/2 Q squared. All right. What are our bounds of integration? Let's say we started with 0 charge. We started with 0 charge, and we're going to go to a maximum value of, I don't know, capital Q charge. Let's write down that integral then. We have the energy U is equal to 1 over C times 1/2 Q squared from 0 to Q. And that's equal to Q squared over 2C. And this is the energy stored in a capacitor. Now, often we can write this as in terms of voltage and capacitance, because Q is equal to CV. So Q squared is equal to C squared V squared. So we can write down the energy U is equal to, if we're doing our math right, 1/2 CV squared. And that is the energy stored in a capacitor. But where is that energy stored? Well, we've built up an electric field. And that means the energy of the capacitor is actually stored in the electric field. We've stored energy in the electric field. What's neat is that when we flip that switch, like we did in that example, that electric field pushes back on the charges and creates its own voltages, or sorry, its own currents, and we get that energy back. We flick the switch one way, the voltage builds up an electric field, and that's where the energy goes. We release the switch, and the field collapses, driving current the other way. It's a conservative force. We've stored energy in the electric field. This is not like resistors, where the energy is lost to heat. We get that energy back. And in fact, in one case, we're doing work on the electric field. We're doing positive work on the capacitor. And then the capacitor is doing work on us in the second cycle, when we're discharging the capacitor. So very neat. So that's a device. A capacitor is a device which stores energy in the electric field. Now, there's one other field in electromagnetism, the magnetic field, and that brings us to our next element, the inductor. So I'll say stores energy in the electric field, like that. Now we're going to move to an inductor, which stores energy in the magnetic field. And just like there was capacitance that we had in electricity and magnetism, we have inductance in electricity in magnetism. And inductance is basically a changing current. And inductance is basically the fact that if we change our field, we collapse a magnetic field, that creates an EMF or a voltage. So a changing magnetic field will drive an EMF, which will create a current, which will create its own magnetic field. This is the principle of inductance. And if you recall, for capacitance and capacitors, the canonical thing was this two pair of parallel plates, because capacitors are all about the electric field. And that's the easiest way to make a nice, convenient, uniform electric field. So the equivalent device for inductors, which are all about the magnetic field, is a solenoid, a coil of wires. And as we have current flowing through it, we get a roughly uniform magnetic field going through that wire there, that coil. So an inductor has a well-defined inductance, L, and the units of L are henries. Actually, Faraday was already working on inductance, but he already got the capacitor, so Henry gets the inductance unit. And typically you have about a millihenry is a good unit. In fact, I have an inductor lying around here, which is really literally a coil of wire. This is a 1 millihenry inductor here, and we can plug it directly into a circuit board. So before, just in brackets, we had, for capacitors, I is equal to C dV by dt. For an inductance, we're going to have V through the inductor is equal to L di by dt. That's the equation defining an inductor. So the circuit symbol for an inductor is a cartoon of a solenoid. Now finally, we can actually derive an equation for inductance the same way that we had an equation for capacitance in terms of geometry. Now we can define the dimensional geometric form of the solenoid, but that's less important in our course. I'll just state it for reference now. The inductance of a coil that has n turns has cross-sectional area A and length L is given by this. Now there's this mu out here. That's called the permeability, and it's another material constant, much like epsilon was for the capacitor. For free space, we have mu naught, which is approximately equal to 4 pi times 10 to the minus 7 henries per meter. Henry per meter. Actually, interestingly enough, a couple of years ago I could have drawn an equals instead of an approximately equals. But since there's a redefinition of fundamental units in physics, mu naught is no longer identically 4 pi times 10 to the minus 7 henries per meter, but only approximately equal to. Okay, so wrapping it up, this is a fairly long lecture. We'll just talk about parallel and series addition of capacitors and inductors. So if I have two capacitors, let's just remember that C is equal to epsilon A over D. Imagine that I had a parallel combination of two capacitors. Well, in this case, I actually have a larger effective area. Suppose the distances are the same. I have a larger effective area, therefore I have more capacitance, and it turns out that the capacitors add just like series resistors do. I get a bigger capacitance. Whereas, let's think about the series connection. Now, what have I done? Well, this middle section here isn't doing a heck of a lot. It's all at one potential. And effectively, I just have a larger distance between the plates. So Finally, for inductors, I just get the case like resistors. So I have two inductors, L1 and L2, in series is equal to just the simple sum of them. And that might seem weird to you because in our equation, L was in the denominator, but effectively we've increased our n, and it's n squared over L. So it kind of we get a bigger benefit from having more loops. And finally, parallel combination of inductors is equivalent to a smaller inductance like parallel resistors. Okay, well this is a long one. This is a big lecture. So let's summarize. The important key points for a capacitor, C is equal to QV, is one way of thinking about it, but it's more convenient for us to write it in terms of current, to think about it in terms of current. And this is our defining equation for a and this is our defining equation for a capacitor. We had RC circuits, and if we connect an RC circuit, it's going to charge, and if we disconnect it and short the resistor to the capacitor, it will discharge. So we have RC circuits that can discharge or charge, and we have the RC time constant, the fundamental constant where T is equal to RC. And energy of a capacitor is stored in the electric field. We also had inductors, and the inductor had the defining equation V is equal to L di by dt. Parallel capacitors yield a larger capacitance, and series capacitors yield a smaller capacitance. It's just the opposite for inductors. And we'll talk about applications of these and how to think of them in terms of continuously changing voltages in the next lecture. All right, thanks for bearing with me.